So in this lecture, we'll give an overview of Monte Carlo methods and spend some time learning about Monte Carlo integration techniques. So the term Monte Carlo is used for calculational techniques that utilize random numbers. And these techniques represent the solution of a problem as a parameter of a hypothetical population and use a random sequence of numbers to construct a sample of the population from which statistical estimates of the parameter are obtained. So, Monte Carlo solution of a problem consists of three parts. So the first would be the choice of the probability density function. Which describes the hypothetical population. The second part would be generation of a random sample of the hypothetical population which is done using a random sequence of numbers. This would be followed by a statistical estimation of the parameter in question from the random sample. Now, of course, if the solution of a problem is some number f, the Monte Carlo estimate of that number will depend on the random numbers used in the calculation. So, this will bring us to a discussion of random number generators. Now, random number generators could be one of two types. There are true random number generators and there are pseudo random number generators. Now, those belonging to the first category, they must be based on random physical processes. So, example could be potential across a resistor which arises from thermal noise, the time between the arrival of two cosmic rays, or the number of radioactive decays in a fixed time interval. But the problem with such generators is that they are very slow, and by their very nature, they are not reproducible. So, it's more preferable to use pseudo-random number generators. Now, pseudo-random number generators, they produce a sequence of numbers calculated by a strictly mathematical procedure. Which nonetheless appear random by some statistical tests. But since the sequence is not really random, there will certainly exist some other statistical test for which it will fail to appear random. Now, several algorithms have been used to produce pseudo-random number generators through computer programs. And the generation proceeds from a seed. So each number in the sequence acts as the seed for the next. Usually there is a provision in different programming languages and tools for the user to set the seed at the start of this program and also to find out what the seed is at the end. So now let's move on to a discussion of Monte Carlo integration. So let's say we want to evaluate the integral from a to b of yx dx. So we'll discuss some Monte Carlo methods to do so. Now, a trivial numerical method which need not be the best method, but a numerical method is to divide the interval from a to b into n subintervals and add up the areas of each subinterval using the value of y at the middle of the interval. So the integration basically becomes a summation of the form b minus a by n, and there is a sum y equals to 1 to n of y at xi, where xi is defined as a plus I minus half b minus a by n. Now, Monte Carlo method, which may seem very obvious at first glance, known as the crude Monte Carlo, basically does the same sum but redefine xi as a plus some ri times b minus a, where these ri's are random numbers uniformly distributed on the interval 0 to 1. More formally, the expectation of the function yx given a PDF fx which is non-zero in a comma b is given as Normally, the available pseudo-random number generators sample a uniform distribution. So, we can take fx to be the uniform PDF for all x lying between a and b. Then, the expectation value simply have this b minus a in the denominator outside, and the mean becomes just the integral divided by b minus a. Similar to the variance, again we must remember that yx is not a PDF. So mu y and sigma y square are the expectation and variance of the function yx for a uniform PDF. Now if we take yi as y of xi, where xi are distributed according to fx, that is uniformly distributed, then by the central limit theorem we know the average of the n values yi approaches the normal distribution for large n. So is the average as the random variable, mean as we have computed the integral by b minus a, and the average standard deviation. Therefore, by generating n values xi distributed uniformly in a comma b and calculating the sample mean, we can determine the value of I by b minus a to an uncertainty of sigma y by root n. Or in other words, I equals minus a by n Another method to evaluate the integral is by something known as hit or miss Monte Carlo. So in this method, two random numbers are required per evaluation of yx. So let's say r x comma y is a random number uniformly distributed on x comma y, and we generate a point in the rectangle defined by the minimum and maximum values of y and the limits of integration a and b. So we generate xi, the rectangle a comma b, yi between y min and y max. Capital R just denotes that it is generating a random number in that interval. Now, if we do not know y min and y max, so then we must guess safe values. And the generated point is called a hit if yi is less than y of xi. It's called a miss if it's the other way around. Then an estimate of the integral is given by the fraction of points which are hits. So I, number of hits, in times b minus a times y max minus y min. Now, since hit or miss is a binomial situation, the number of hits follows the binomial PDF. With expectation n times p, as we have derived before, and similarly variance n times p times 1 minus p, where p is the probability of a hit. The variance of the integral is trivially related to the variance of the number of hits. So we have vi equals 1 by n square v n hits times b minus a square times y max minus y min square, which can be rewritten as 1 by n. So there is a factor of n in the expression of variance. It's p times 1 minus p times b minus a square, and lastly y max minus y min square. The probability p of a hit can be estimated. So we put a hat to denote that this is just an estimation. N hits by n. So therefore, putting this together, we can write the integral as its mean value basically. One historical example of this is what is known as Buffon's needle. So this was an early 1771 application of 1777 application of the Monte Carlo technique to estimate the value of pi. And this calculation basically proceeds as follows. So one draws parallel lines separated by distance d on the floor. A needle of length d is dropped on the floor such that its position and its orientation are both distributed uniformly. And if the needle lies across a line, we have a hit, otherwise a miss. So we have a scenario like this. Let's say this is d. So now the characterizing features are both theta, the orientation, and the distance of the center of the line with the nearest line. For a given theta, the chance of a hit is given by the conditional PDF. This is the projected length of the needle on a perpendicular divided by the distance between lines. It's basically d cos theta by d, or in other words, just cos theta. So the chance of a hit, irrespective of theta, is then given as theta can go from 0 to pi by 2. We take this conditional probability and multiply it by f theta and integrate over the range of theta values. So f theta is just the uniform distribution 1 by b minus a. The b is pi by 2, a is 0. And so this ultimately comes out as 2 by pi. So an estimate of 2 by pi is given by the estimator of P. So the estimator of P is the number of hits by n. So therefore we can obtain pi as 2 times n times the number of hits. Now one thing we must address is the accuracy of Monte Carlo integration. So let's say, staying with the Buffon's needle example, in crude Monte Carlo, mu of y, which also comes out as the integral by b minus a, is 2 by pi. And the variance is an integral over cos square theta this time minus the square of the mean. So this comes out as half minus 2 by pi whole square. So numerically this is 0.0947. So the uncertainty of the estimation of I is square root of this variance divided by root n, or 0.308 by root n. So this was the result for crude Monte Carlo. On the other hand, with hit or miss, we had the variance 1 by n p times 1 minus p times pi by 2 whole square, which comes out as 0.571 by n. Therefore, the uncertainty of the estimation is .756 by root n, which is considerably larger, so more than a factor of 2 than for crude Monte Carlo. Now one can tabulate the uncertainty of Monte Carlo integration and compare it with that of numerical methods. So let's say we put a list of methods. So there is Monte Carlo, and there is the trapezoidal rule, Simpson's rule, and lastly we have m-point Gauss rule. First, let's look at the 1D scenario. On the other hand, of the d-dimensional case, so we see that the Monte Carlo integration converges much more slowly than the other methods, particularly for low numbers of dimensions. Only if the number of dimensions is greater than 8, only then we see that the Monte Carlo converges faster than the Simpson's rule. But there is always a Gauss rule which converges faster than Monte Carlo. But the rate of convergence is not the only consideration we should have in mind when trying numerical methods. First of all, it's a question of feasibility. So for example, in 38 dimensions, a 10-point Gauss method converges at the same rate as the Monte Carlo, because you see 2m minus 1 by d for m equals 10, d equals 38 equals half, which is exactly the exponent we have in the denominator for the Monte Carlo. However, in the Gauss method, the number of points is fixed. So, number of points and the evaluation of even a very simple function requires on the order of microseconds on a fast computer. So 10 to the power 38 is not feasible. Another problem with, so it would be preferable to use Monte Carlo. Now, another problem is the boundary of integration. So if the boundary is complicated, numerical methods become very difficult. But this is easily handled in Monte Carlo. One simply takes the smallest hyperrectangle that will surround the region of integration and integrates over the hyperrectangle, throwing away points that fall outside the region of integration. Even though this leads to some inefficiency, but this is quite straightforward and one of the chief advantages of the Monte Carlo technique. Another practical issue could be growth rate. So if you perform an integration and decide that it is not accurate enough, with Monte Carlo we just have to generate some more points. However, with the Gauss rule, you have to go to higher order m. And again, going to higher order m poses the same problem that we have described before. Now let's discuss some variance reducing techniques. Monte Carlo integration converges rather slowly with n compared to better numerical techniques. But there are several methods of reducing the variance of the Monte Carlo estimation. So one approach is known as stratification. So in this approach, we split the region of integration into two or more subregions. For example, for two subregions, the integral becomes the variance in this case is just the sum of the variances of the subregions. A good choice of subregions and number of points in each region can result in a dramatic decrease in VI. However, to make a good choice requires knowledge of the function, because a poor choice can increase the variance. In any case, some improvement can always be achieved by simply splitting the region into subregions of equal size and generating the same number of points for each subregion. So this can be illustrated for the case of two subregions using crude Monte Carlo. So the variance for the entire region is given as for two equal regions, the variance is the sum of the variances of the two regions. So we denote this by V2I. This is B minus A by 2 whole square by N by 2. And this will be done for two regions. Notice we are talking about two equal subregions, that's why we are not separately writing C minus A and B minus C, because we have identified that the length of those regions is just B minus A by 2. And this expression can further be simplified to write so the improvement in the variance is just the difference of V2 and V1, and this is given as so if you substitute A let's identify this integral as A, this integral as B, and we can rewrite, sorry, this should be V1I minus V2I. And this is certainly greater than equal to 0. So some improvement in the variance is attained, even though it may be arbitrarily small. And this improvement can be qualitatively understood as due to an increased uniformity of the distribution of points. Another approach is what is known as importance sampling. So we have seen in crude Monte Carlo, the variance of the estimate of the integral is proportional to the variance of the function being integrated. So the less variation in y, that is more constant yx is, the more accurate the integral. So we can effectively achieve this by generating more points in regions of large y and compensating for the higher density of points by reducing the value of y accordingly. The same was the motivation for stratification. So in importance sampling, we change variable in order to have an integral with smaller variance. So if we start with I, goes from A to B, yx dx. Let's say we rewrite this as yx by gx times gx. Where g of x capital G of x is identified as the integral from a to x of small gx dx. So we must find a function gx such that gx is a PDF everywhere. Gx is a PDF and it's everywhere positive and normalized such that G at B, capital G at B equals 1. Second requirement is that capital G of x is known analytically. Then either the condition that capital G of x can be inverted or a random number generator is available which generates points according to small g of x. Another important point is that the ratio y of x by g of x should be as nearly constant as possible. And in any case, more constant than the original function y of x. Basically meaning that the standard deviation of y by g should be less than the standard deviation of y. We then choose values of capital G randomly between 0 and 1 for each g. Solve for x and sum over y of x by g of x. Now, although importance sampling is a useful technique, it suffers from a few drawbacks. First of all, the class of functions g which are integrable and for which the integral can be inverted analytically is small. So typically such functions are only trigonometric functions, exponentials and polynomials. While the inversion could in principle be done numerically, but that introduces more inaccuracies which may be larger, that the gain made in reducing the variance is nullified. Importance sampling is very difficult. Once you have more than one dimensions. It can be unstable. So if small g becomes small in a region, then that would prompt y by g to become very large. And as a consequence of that, the variance also becomes very large. So it's dangerous to use a function g, which is 0 in some region or which approaches 0 rapidly. Now lastly, y of x itself should be well known in order to choose a good function. G. Although one advantage of this method is that the singularities in y of x can be removed by choosing a g of x having the same singularities. So this is where we'll end our discussion on Monte Carlo integration. Next time we'll look into Monte Carlo simulations.